Hey everyone, welcome back to physics. This is going to be lecture 20 of the course, and in this section we're going to continue with our application of Newton's laws, and we're going to look specifically at problems that involve frictional forces. So let's go ahead and jump into it. We'll call this section 4.3 frictional forces. So we've talked about friction already. We spent some time on it several lectures back. But just to review quickly, just to make sure we're clear on the notation and all of the different concepts here, we've got essentially two different kinds of frictional forces. We've got static friction, which we'll denote F sub s here, and kinetic friction, which we'll denote F sub k. Okay. And so for the static friction, we say that static friction is less than or equal to mu sub s times, and here I guess we're saying the magnitude, is less than or equal to mu sub s times the normal force, the magnitude of the normal force. And this is our static friction. And static friction, the idea here is that it will vary depending on the force it is resisting. It's very similar to the normal force in that respect. So as the weight of an object increases, the amount of normal force required to keep it in equilibrium vertically increases as well. Unlike the normal force, well, in general, the normal force isn't limitless, but it doesn't have a fixed, it doesn't always break down like static friction. Static friction is going to vary between 0 newtons. The magnitude of static friction is going to be greater than or equal to 0 newtons. And it's going to be less than or equal to this quantity here. So this really represents the maximum static friction. Okay. Now, once this force is exceeded, static friction force is overcome and kinetic friction takes over. So once this level is reached by whatever the opposing force is, the object becomes unwedged, and it starts to slide. And once that happens, you have the other kind of friction, which is called kinetic friction. And so the kinetic friction, the magnitude of the kinetic friction is equal to mu sub k times the magnitude of the normal force. Right, so very similar, just different coefficients on the front here. So this is the static coefficient, this is the kinetic coefficient. Okay, and then when we talk about kinetic coefficient or kinetic friction, we're talking about movement. Kinetic implies movement. And here specifically we've got two surfaces sliding together. Okay. And so you can see just kind of by the way this is set up that the magnitude of the kinetic friction force is going to increase as the weight of an object increases. Okay, so the heavier the object, given the same kinetic coefficient, the more friction it's going to generate, right? And the easiest example here is to think of like a box full of books. If I take a cardboard box and I sit it on like a tabletop, there's a certain amount of friction. There's a friction coefficient between the tabletop and that cardboard box. Now, if I load it full of books, you can just think it's going to be harder for me to slide it against the table, isn't it? Versus when it's empty, right? And so that's the relationship you see here between the with the normal force. Okay, and so here we've got sliding surfaces, and here we've got stationary. Okay. Now these coefficients are going to vary. The values of mu sub s and mu sub k are going to vary depending on the material. And so just as an example, some materials you might encounter in the real world might be like steel on steel. Right? So like a steel plate sliding against a steel tabletop. Right, so for something like that, you might see a mu sub s and a mu sub k of, I don't know, maybe 0.75 and maybe 0.58, right? Maybe glass, like a glass object sliding on a glass tabletop. Right there you might see a slightly different, so 0.94 perhaps, and maybe 0.40. Okay, and so in general, the kinetic friction coefficient is going to be less than the static coefficient, right? And this is something that we talked about this earlier, but this is something that is borne out by experience. If you place something on a surface and something relatively heavy and you start pushing on it, you'll notice that it takes a little more effort initially to get the thing moving than it does to keep it moving once it's moving. And that is going to be the relationship between these two coefficients. Now, something that's got a ton of friction would be like rubber on concrete. Right, this is literally like your car tire on the road. So maybe we say the static coefficient there is 1, and the kinetic coefficient is 0.8. Right, it's easier to slide a tire that's in motion than it is to slide a tire that's stable on concrete. Right, and of course, there's a whole bunch of you can any two surfaces you can conceive of, you could generate some kind of a coefficient on. And we'll see in an example in a second how that kind of thing can be done. Let's take a look at another chart that just I want to underscore the relationship between these two types of friction and force. Right, so let's imagine that I've got a chart here. Right, and this axis is time, and then this other axis is some force that I'm applying, which I'm just going to call push. Right, so let's imagine that you got a stationary object with a steadily increasing force. So I've got some object just at rest, and I'm applying some force to it. The object is initially at rest, and just imagine idealized circumstances where this pushing force can be increased continuously and uniformly. Right, so I'm just uniformly increasing this pushing force until the object starts to move on the surface. Okay, so there's going to be a period where there's no motion, because remember, this force starts at 0 and it's going to be applied until the object starts to move. Okay, and so I apply some force, I apply some force, I apply some force, I apply some force. No movement yet, but then we're going to hit this level. And what is this level? This is the level that I'm going to call the static friction max. All right, once that level is hit, then the object goes from having no motion to moving. All right, so I apply a force, no motion. Apply a force, increase the force, no motion, no motion, no motion, no motion, no motion. And then suddenly, the force is steadily increasing. Suddenly, the object starts to slide. Now, what's taken place physically is the force is increased up until the pushing force hits and exceeds the static friction force. Okay. Right, and so that's what we call the static friction max. Now, once that happens, we know from what we just discussed that this kinetic coefficient is less than the static coefficient, which means that the friction force decreases rapidly, instantly, really. And so what happens then is that the force required to push the object to keep it steadily moving diminishes. And what is that level? Well, that is the kinetic friction force, right? So the object is not moving, the pushing force increases, it hits a certain point, and then it jars the item loose, and then the object moves with a different friction force, right? And that's exactly how this works. So go get like a little brick, stick it on your concrete slab, and just try with your hand, to increase the force gradually and uniformly, and you'll notice once the object starts moving, the amount of force required to keep it moving steadily is less than the force you applied to get it started. Okay, and so that is kind of a little bit of more detail on how that works. Now let's take a look at some examples. We'll spend the rest of the time looking at some examples. And we really are just trying to explore different things about friction, just pull different friction scenarios into problems. And this is by no means exhaustive. We could never in these lectures exhaust the different types of problems that you will come across regarding these physics concepts. So here's a good example though, just to start with. You pull a 500 Newton crate that is at rest in your driveway. All right, so you got this crate sitting on your driveway. You've got a rope around it. Well, we can draw a picture. You've got a rope around it, and you're just dragging it across the driveway. All right, so it's just dragging across the surface. Okay. Now, to get it sliding, you need to pull with a force of 230 newtons. You know this somehow. You've got some kind of a measuring device. You can measure the force being applied. So to get it started, to get it sliding, you need to pull with a force of 230 newtons. Yeah, once it's sliding, you need only apply 200 newtons to keep it moving. Okay. Now the question is, what is mu sub s and mu sub k? Right. So what are these coefficients? Right, and this is probably very similar to the way these coefficients are derived in practice. Right. If I take I've taken an object, lay it on another object, and try to slide them. One way to derive these coefficients is to just attach some kind of a force sensing device, some kind of a force meter, and I can keep track of how much force is required. And the calculation is pretty straightforward. Let's look at the static coefficient first. Let's look at the static coefficient first. Now, what does the free body diagram look like? Well, I've got this crate. There's a weight here of 500 newtons, and I'm just going to use basic notation. I'm not going to worry too much about the vectors. And there's a normal force opposing that of 500 newtons as well. Right, I'm pulling on the crate, and this, the way that we're going to figure this out is we're going to think about the crate, the free body diagram at the instant, just the instant before the crate begins to slide. Okay, so basically we're trying to max out that static friction force. Okay, so this is going to be, there's going to be a pull here, and I'm going to put it at 230 newtons, but maybe it's 229.99995 or something. I'm going to write 230 newtons though. Okay, and I've got some static friction force that represents something very close to the maximum. Okay. Now, well, we're interested in the horizontal motion. We're trying to figure out what the coefficient of static friction is. So we're going to be looking at the forces in the x direction here. So what are those forces? Well, you've got the pull, and you've got the static friction max value. And those two, I mean, right before movement begins, they need to be equal to 0, right? We're at equilibrium. There's no acceleration. Right, and so this is very simply telling me that the force of the pull equals the max static friction force. Right, that's what we're seeing here. Right, and so let's break that down into its pieces. So this is really telling me that 230 newtons, the force of the pull, is equal to mu sub s times the magnitude of the normal force. We know the magnitude of the normal force is 500 newtons, right? And so 230 newtons is equal to mu sub s times 500 newtons. Right? And so then it's just a simple mu sub s must be equal to the ratio 230 newtons over 500 newtons. Right? And if you do that arithmetic, you'll see that that's 0.46. Right? And so your static coefficient is 0.46. Now, how does it work for the kinetic coefficient? Well, very similarly, right? Let's take another free body diagram here. I've got, again, the normal force, 500 newtons, and that's opposing the weight of the object, 500 newtons. Okay. I've got the pole, this time, right, because the object's moving, I'm interested in exerting a force that keeps the acceleration zero, just keeps this thing moving at a constant velocity. And that would be, well, we're told it's 200 newtons. Presumably you can measure that. And that's opposing a kinetic friction force. Okay. And so similarly, here we would have the sum over the x direction would be equal to F pole minus kinetic friction. And the velocity is non-zero, but the acceleration is zero, so we're in equilibrium. And so that means the pole is equal to F sub k, which implies that 200 newtons is equal to mu sub k times the magnitude of the normal force, which means that 200 newtons is equal to mu sub k times 500 newtons. And so here we'll see that the kinetic friction coefficient is 200 over 500. Right? And if you do that math, you see it's 0.4. Okay? So that's how you can, given the pulling or pushing forces that generate equilibriums, both equilibriums with zero velocity and equilibriums with non-zero velocity, that's how you can generate the static and kinetic coefficients. Okay, very good, very good. Let's take the same example and explore this static friction concept again. So let's consider same scenario as above. Same scenario as above, but let's assume only a 50 Newton pull. Okay, what's going on in this scenario? What happens in a scenario where we're pulling at only 50 newtons? Right, I think we can all guess, but let's look at what the math tells us. So I've got 500 newtons here, and normal force 500 newtons that direction. All right, this time I'm pulling on it with a smaller force, right? So only 50 newtons. Right, and the question is, what's this? Right, we know there's some kind of friction. It's static or kinetic. What is it? Well, we know from the previous example that the static friction force, the maximum value of that is 230 newtons. We calculated that on the previous, or actually we were given that. And then we used that to calculate the coefficient. But so let's think about what this, if we use this value, what does the scenario look like? So we take the sum of the forces in the x direction. Those are going to be equal to the force of the pole minus the static friction force max, here we would say, and that's 50 newtons minus 230 newtons. Right? So you do that math, you see that this is negative 180 newtons. Now, that's kind of unintuitive. That doesn't make sense. And that's because we're really applying this thing here incorrectly, right? This is not quite right, right? Remember, the static friction force is dynamic. It responds instantaneously to the force it's opposing. So if my pulling force is only 50 newtons, then my static friction force will only be 50 newtons, right? And it'll increase as my pulling force increases, right? So this is not exactly what's happening here. So what's really happening is something more like this. I've got my force of my pull, and I know that there's static friction involved because I know that the thing is sitting at rest. And therefore, these are all equal to 0. And what's really happening here is my pulling force is equal to my static friction force, right? So 50 newtons, 50 newtons. So basically what's going on in this scenario is that the crate is just sitting there. It's sitting there, and it's going to be sitting there for a while, a long time, until you dramatically increase this force. Okay. All right. Very good. So just another example of how that static friction force varies dynamically as the force it opposes increases or changes. Okay, another example kind of based on this one. So what if we pull on the rope at an angle other than horizontal? What if we pull on the rope at an angle other than horizontal? What happens then? Say we pull at an angle of 30 degrees above horizontal. .30 degrees above horizontal. Okay. So let's draw the picture. So here I've got my crate, right? And I've got still weighs 500 newtons. I've got a normal force here. We'll figure out what that force is. Let's say the thing's in motion. But instead of pulling directly horizontally, I'm pulling kind of at an angle here. So F pull is a little angled, right? And let's say specifically it's 30 degrees. And so you can imagine like this kind of a triangle. Right, and so how hard do we have to pull to keep the crate moving at a constant velocity? So let's say we've got some kinetic friction here. How hard do we have to pull in order to keep the crate moving at a constant velocity? Okay, so a couple of things here, right? That there's a couple of things to think about. When I pull at an angle, then the force of my pull is now no longer opposed merely by the kinetic friction. Also, the weight of the object is opposing my pull, right? And so the key here is to see that the normal force, this guy up here, is now being offset or aided, I guess, by the pull, right? And when I aid the normal force, I'm in a sense kind of lifting the block or the crate up off the ground a little bit, and that's reducing the friction force. Okay, so the key here, and however you want to phrase this, is that the normal force has changed, right? And that means the friction force is also changed, right? Remember that kinetic friction force is equal to mu sub k times the normal force. So if the normal force is decreased in any way, the friction force is going to be decreased. And conversely, if I increase the normal force, I increase the friction force. Okay, and so this is a great problem because, I mean, you've all had this experience. If you say you've got a really heavy crate like this and you're dragging it across the driveway, you don't get right down and pull it horizontally. Well, maybe you do. But more often you're kind of up at an angle and you're sort of pulling it in a direction, but it's not purely horizontal, right? So you're not opposing merely the friction force, but you're also opposing weight of the object to some extent. Right, and sometimes you maybe have noticed that if you lift it off the ground a little bit and then pull, you can break through that initial static friction a little bit easier. Okay, Well, let's break down this triangle here and see if we can redraw this in a way that's a little more intuitive. I think I'll flip the page here. So here's how I would, let's break down this triangle. Let's start with that. All right, so I've got this triangle, it's at 30 degrees, and here's the force of the pull. Okay, and we'll call this X, and we'll call this Y. And so sine of 30 degrees is equal to Y over the hypotenuse, which is F sub P, and cosine of 30 degrees is X over FP. Right, and so therefore Y is F sub P sine of 30, and X is F sub P cosine of 30. So whatever the pull force is, it's going to be kind of scaled by this sine and cosine of 30 degrees. Okay, so now let's revisit the free body diagram. So here I've got the weight of the object. That's unchanging. It doesn't matter how hard I pull on this thing. It's still 500 newtons. Right, now the horizontal force here in the x direction is F sub P cosine of 30 degrees. And that is opposed by a kinetic friction force. And I've got a normal force pulling upwards, but I can't say that the normal force is 500 newtons because I've also got this thing, right? I've got this other force that is due to me kind of lifting the block ever so slightly because of the angle that I'm pulling, right? And so this is going to be F sub P sine of 30 degrees, okay? And so this is a bit more like the way we want to think about the free body diagram. Now let's assume that the object is in equilibrium. It's got a non-zero velocity, but the acceleration is 0. So let's break out our equations here. So we'd say that the sum of the forces in the x direction would be, well, you've got this Fp cos 30 minus the kinetic friction. Okay, and now technically I'm going to rewrite Fp cos 30, and I'm going to rewrite the kinetic friction as mu sub k times the normal force. And that needs to be equal to 0. Okay. And what's going on in the y direction? Well, in the y direction, I've got Fp sine of 30 plus the normal force, whatever it happens to be, minus the weight. And that has to all equal 0. Okay. So these will be our starting points. These are the equations that kind of describe this scenario. Let's drop in the known quantities. So I've got Fp, F sub P cos 30 minus, and I know the kinetic friction coefficient is 0.4, and times the normal force, right? In my notation, you just have to bear with me, I just mean the magnitude of the normal force, right? Although this is the normal force in the x direction. And then similarly, we've got Fp sine of 30 degrees, right, plus this normal force, and then minus the weight, which is 500 newtons, and that equals 0. So I've really got this system here where what do I have? I've got Fp is unknown and the normal force is unknown. So two equations, two unknowns. I can solve this. Okay, so I'm going to start by I'll just label this 1 and 2. I'm going to rewrite 2. So I'm going to rewrite 2 as the normal force is equal to 500 newtons minus this F sub P sine of 30 degrees. Okay, and then what I can do is I can take this quantity here, toss it into the first equation, and then solve for F sub P. So we'll take 2 and plug it into 1. Okay, and so I get F sub P cosine of 30 degrees minus 0.4 times the normal force equals 0. Okay, so that's F sub P cos 30 degrees minus 0.4 times this 500 newtons minus F sub P sine of 30 degrees, and that equals 0, right? Okay, well, let's see. F sub p cos 30 degrees minus 0.4 times 500 newtons plus 0.4 times F sub p sine of 30 degrees equals 0. And I can factor the F sub p out. That's really what I'm after. All right, so I could say F sub p, and then I got cos 30 degrees minus 0.4 sine of 30 degrees. And that's going to equal this thing over on the other side. All right, and then I can just do the division, right? So F sub p is equal to 0.4 times 500 newtons divided by cos 30 degrees minus 0.4 sine of 30 degrees. Okay, and I can, those are all known values, so I can calculate that. And when I do that, I get about 188 newtons. Okay, so in order to maintain equilibrium, i.e. to keep the velocity constant, the force of the pole that's 30 degrees above horizontal must be 188 newtons. Right, so but remember before when I was poling purely horizontally, right, I was 200 newtons were required. Now you can see, because I'm poling at a bit of an angle, I'm reducing the friction, and therefore I can pull a little lighter. I don't have to pull quite so hard, right? And this is all kind of coming through because the normal force is being impacted here, right? And so what does this off horizontal force do to the normal force? So what about the normal force? Right, and so if we think about what we had that equation 2, it was F sub p sine of 30 degrees plus the normal force minus the weight equals 0. Well, I can just substitute in my 188 here, can I? So 188 newtons times the sine of 30 degrees plus the normal force minus 500 newtons equals 0, and I can therefore solve this, and the normal force must be 500 newtons minus 188 newtons times sine of 30 degrees. And when you do all of that, you get 500 newtons minus about, well, I don't know what it ends up to, but you get 406 newtons. Right, so the normal force is offset slightly. So by pulling up slightly on the rope, we reduce the magnitude of the normal force. Right, and so in reducing the amount of the normal force, we reduce the amount of the friction, and that's really what allows us to pull with less force and keep the thing moving. Okay, very good. All right, so kind of a nice, interesting problem, more in line with what you would experience in your everyday sort of scenario. And a fun follow-up problem would be to try to figure out what is the optimal angle. Right? What is the angle that minimizes the amount of pull required? Right? It's probably not 30 degrees. What is it? See if you can figure out how to do that. Okay, another example. So a couple lectures back, we had this sled example. We had a sled sliding down a hill. Right? This time we're gonna kind of play with that idea again. So you got a sled sliding down a hill. A sled is sliding down a hill. Sorry about that. The sled has some friction. I think in our previous example, we didn't have any friction. This is the friction section, so let's talk about some friction. The sled has some friction. Assume the sled is moving at constant velocity. So we got an equilibrium. Assume the sled is moving at constant velocity. Okay, and we want to derive an expression for the slope angle as a function of the sled's weight and the friction coefficient. So, so we want to derive an expression for alpha, the slope angle, as a function of the weight and mu sub k. Okay, okay, the coefficient of kinetic friction. Now remember what's going on here. Right, we've got a sled on a slope, and it's sliding down the slope naturally. All right, in the previous example, we had some value for the slope. Just imagine the slope is very, very long, so we've got a certain amount of time where we can keep an eye on this. But in this case, the sled is sliding down the slope, and we're interested in constant velocity, right? So there's some force pulling it down, namely gravity, and then you've got some friction force on the other end. And so what we want to do is we want to derive an expression for alpha, the angle that keeps the velocity constant, right? And we want this expression to be a function of the weight of the sled and of the friction between the sled and the slope. Right, so obviously if the slope is just like solid ice, then the alpha has to be much smaller in order to maintain equilibrium. But if the slope is very, very slushy and almost muddy, then it has to be a lot higher to keep the sled from grinding to a halt, right? So that's the idea. Okay, so let's put together like a little free body diagram, try to remember what this thing is, what's going on here. So I've got the sled on the slope, and it's got a weight pulling it down. Now it's headed down a slope, and so I've got some force kind of pulling it down. I've also got a normal force that opposes perpendicular to the slope. Remember, that's how that works. And then I've got some friction forces. In this case, it's kinetic friction. Okay. Now, what's really happening here is that I've got kind of a triangle scenario here. This is our alpha right here, and this is a right angle. And so this would be whatever the weight is times cosine of alpha. That's this leg. And this would be W sine of alpha. That's this leg. And that's really what this is. Okay, the weight of the object times sine of whatever the angle alpha is. That's what's pulling it down. And we'll coordinatize it so that this is the x-axis, and this up here, that's the y-axis. Okay, so we've got kind of an x-y orientation here. Okay, so let's assume equilibrium, right? The sled has a velocity, but it's not accelerating. So assuming equilibrium, what do we got in the x direction? The sum of the forces in the x direction would be equal to, well, you've got this W sine of alpha, and we'll take that to be the positive direction, minus the force of kinetic friction. Okay, and we can rewrite that as W sine alpha minus mu sub k times the normal force. And that needs to equal 0, right? Remember, there's no acceleration, but we have velocity with no acceleration. So Newton's first law says that this sum of the forces need to equal 0. Similarly, in the y direction, what do we have? Well, we've got this force here, W cos alpha, and then we've got the normal force. So we'll take that to be negative. So negative is down, positive is up, and those need to be equal to 0. Okay. Okay, so let's just rewrite this slightly. So I've got two equations. The first one is W sine of alpha minus mu sub k times the normal force. That equals 0. And the second equation is the normal force minus W cos alpha equals 0, right? So I've got these two. Okay, so well, we're not trying to solve here. We're trying to derive an expression for alpha. Really, that's what we're after, right? We're trying to derive an expression for alpha. So we want to solve for alpha. All right, I'm just going to take this guy here real quick, and I'm just going to make this, the normal force is equal to W cos alpha. Now what I'm going to do is I'm going to take that, I'm going to stick it in here for the normal force here. I'm going to plug that in there. So I get W sine of alpha minus mu sub k times, and I'm going to plug this in, W cos alpha and that's got to equal 0. Okay. Well, that means W sine alpha equals mu sub k times W cos alpha, right? Which means, and I can do some arithmetic, I can do some algebra here, and I can see that mu sub k equals W sine alpha over W cos alpha. The W's cancel, the weight cancels, and I get sine of alpha over cos alpha, which, if you recall, is tangent of alpha. Okay. And so alpha, as you know, so remember we're trying to solve for alpha, so I just have to take the inverse tangent here. Alpha is equal to the inverse tangent of mu sub k, which is kind of interesting, right? So the angle needed to maintain equilibrium doesn't appear to depend on the weight of the sled at all. It's really just the inverse tangent of whatever the kinetic friction coefficient is. Right? That's a little unintuitive. You might have thought like, oh, the angle depends on how heavy the sled is. Well, not really. All that really matters is that kinetic coefficient, right? So as the kinetic coefficient changes, the angle needs to change, irregardless of whether the sled is very heavy or very light. Kind of an unintuitive result, but I think if you think about it, you can see that all those things are related anyways, and the kinetic coefficient is really the underlying piece. Now for the last problem, let's think about the same setup, but this time let's assume that the sled is accelerating. Consider the same setup, but let's assume that the sled is accelerating. Okay. So it's accelerating down the hill. Right, in this case, let's try to derive an expression for the acceleration as a function of the other variables. Let's derive an expression for A as a function of the other variables. Okay, and so this is very similar to what we just did, right? You've got the weight of the sled, you've got the normal force, you've got the force pulling it down the hill, which we saw was W sine alpha, and you've got the kinetic friction opposing it, the sled's in motion, and then you've got this W cos alpha, which is offsetting the normal force. Okay, now again, this is the x direction, and we'll make this the y direction. Okay, now given how we've coordinatized the problem, we're assuming here that the sum of the forces in the x direction are non-zero, right? Meaning it's accelerating down the hill. But the sum of the forces in the y direction is still in equilibrium, right? So it's not accelerating into the hill or coming off of the hill in any way. So those are still equal to 0. So kind of a subtle point, but important, right? Important. So again, we'll have two equations here, and we're going to start with the sum of the forces in the x direction. And just like before, it's W sine alpha minus mu sub k times the normal force, except now it's not equal to 0. It's equal to the mass of the sled times the acceleration in the x direction. Okay, that's the first equation. The second equation is the sum of the forces in the y direction, so they're equal to the normal force minus W cos alpha, and these are equal to 0, right? Remember what we said here. The sled is not accelerating into the mountain or being accelerated off of the mountain in a vertical direction. It is stationary in equilibrium in that respect. It's just accelerating down the hill, right? Not off the hill. Okay. So my two equations are W sine alpha minus mu sub k times the normal force equals m times the acceleration in the x direction. And my second one I'm going to write as n equals W cos alpha. Okay, so again, you can probably guess. I'm going to take that cos alpha and I'm going to substitute it into equation 1 for the normal force, and then we'll have things simplified somewhat. Okay, so I've got W sine of alpha minus mu sub k. Now instead of the normal force, I'm going to plug this in, so W cos alpha, and that's equal to mass times the acceleration in the x direction. And so I want to solve for a, right? I'm solving for the acceleration, so I'm actually almost there. I've got W, I'm going to write a sub x is equal to W sine alpha minus mu sub k W cos alpha all over the mass of the sled. Now, you could be done here, technically, but there's a better way to do this. If you notice that the weight is in both terms, and both terms includes an m, therefore we can do some cancellation. And so this is mg sine alpha minus mu sub k mg cos alpha all over m, so the m's will all cancel out, right? And so we could say that a sub x is equal to g, gravitational acceleration, times sine of alpha minus mu sub k g times cosine of alpha. Okay, I guess you could write it as g, let's do it like this, sine alpha minus mu sub k cos alpha. I guess that's the simplest way to write it. Okay. So the acceleration in the x direction is a function of basically, in this case, just the kinetic friction coefficient and the angle of the slope. So let's try a couple of values here. Let's let mu sub k equals 0.1, kind of like an icy hill, something like that. And let's see what we get here. And so let's try let's try the kind of an edge case here. Let's say alpha is equal to 90 degrees. What do we see? What's the acceleration look like? Well, a sub x would be equal to 9.8 meters per second squared times sine of 90 degrees minus 0.1 times cosine of 90 degrees. And so that's 9.8 meters per second squared times, that's 1, minus 0.1 times 0. So it's just 9.8 meters per second squared. Does that make sense? Yeah, basically, I mean, alpha is 90 degrees. That means the slope is a cliff. And actually, the sled isn't sliding, it's just falling. Okay, so that's kind of a border case. What about if the slope is a little more like a slope? What if it's 40-degree slope? In that case, the acceleration would be 9.8 meters per second squared times the sine of 40 degrees minus 0.1 times cosine of 40 degrees. Okay, and so you get something like sine of 40 degrees is 0.6428, cosine of 40 degrees is 0.766. And so when you do the arithmetic inside here, you get 0.5662. So about half of free fall and about 5.55 meters per second squared. Right, so this is a function that tells you, inputting whatever the coefficient of kinetic friction is and inputting the steepness of the slope, it tells you what your acceleration is gonna look like. Okay. All right, very good. I think we'll end with that example. That was a nice review of some of the ideas of friction and elaboration on some problem types that we probably haven't seen before. In the next section, we'll do something similar, but we'll kind of delve into circular motion. So look at some specific examples of applying Newton's laws to circular motion. All right, until then, take care.